Hi everybody, welcome to your first lesson in calculus. We're going to look at the concept of instantaneous rate of change in our first lesson. We looked at all kinds of rates of change in our lives, like how fast we're growing, how much money's in our bank account, how fast we're driving our cars. All kinds of things are rates of change. In physics, we talk about velocity, and when you consider an object that travels in a straight line, when you talk about average velocity over a given time interval, we can define that as a ratio in the change in position compared to the change in time. So the displacement or the net change over that elapsed time period. That little triangle, that's the Greek letter for change. It means difference or displacement. When we think about velocity, though, in a physics term, often we mean instantaneous velocity. And that's the speed and direction at any given time, and a moment in time, at an instant. But that's kind of hard to do, because if you're using a ratio to define instantaneous velocity, that ratio is going to cause division by 0. And we can get around that in calculus by estimating instantaneous velocity on a very, very small time interval. So we can generalize that by saying average velocity over a very small time interval is going to give us a really good approximation of instantaneous velocity. So let's take a look at that in a practical sense. Let's say we climb to the top of the Tower of Pisa and we drop a coin to the ground. And we want to use Galileo's formula, which is 16t squared. So I'm going to enter that here in my calculator, 16t squared. And we want to compute the average velocity in feet per second over the time interval in the table. And the first one's done for us. So I can replicate that here by taking the function value at 0.71 of a second and subtracting that from the function value at 0.7 of a second and dividing by 0.71 minus 0.7. And we get 22.56 feet per second. So if we continue that, I can copy and paste this, changing our time interval to 0.705. And the denominator, changing that to 0.705. We have 22.48 feet per second. So you can stop the video and calculate the other values and then come back to see if you have the same answers I have. So in the final calculation, I got 22.400 feet per second at that time of 7/10 of a second. Our coin was falling at this rate at that instant because we took our neighborhood and made the neighborhood very, very close to 7/10 of a second. Just a word about the AP exam. You want to always have 3 digits behind the decimal. Don't round until you get to the very end, but always have at least 3 digits behind the decimal. Okay, so in calculus, the study of rate of change is a fundamental principle to our study in calculus. In our first example, we let the time interval shrink to 0 so we could see the average velocity converged to the instantaneous velocity, or that the instantaneous velocity is the limit of the average velocity. Limit's going to be a word you're going to love. So graphically speaking, the average speed or average rate of change is defined by the total distance traveled divided by the elapsed time period. And here you can see that symbolically again. So graphically, if we sketch the secant line, I've already done that on my example. You can stop and do this on your example. We want to estimate the average velocity, and I'm going to use this point here, which is 1, 3, and the other point at B, which is 4, 4, and here's my secant line. This line here is my secant line. M secant is the average rate of change, is the slope of the secant line, and we're passing through 4, 4 and 1, 3. So our average rate of change, or average velocity, is a 1 to 3 ratio. While instant velocity is the slope of the tangent line, and we need calculus to determine that exact answer, but we can estimate it. And again, I've drawn my tangent line here. I want the slope of that tangent line, and it looks like I've hit a point here, and I want the slope right here, which is at 2, 2, 4. But my tangent line also extends over here to 5, 6. So we could estimate our instantaneous rate of change as the slope of the tangent line, which is about, what is that, a 2 to 3, rise is 2, run is 3, is it about 2/3? So we've got an estimate for the instantaneous rate of change. Again, because I can't find a slope at 2, 4, since I'm going from 4 to 4 and from 2 to 2, that gives me 0 over 0. That's not allowed. In this example, we're talking about taking a spin class, and we want to know after the class is over, you've got a rapid heart rate. And over time, your rate is going to go down as you are finished exercising. So let's write an expression for the rate of change of your heart rate from when you first stopped exercising to 90 seconds after you stopped exercising. And you can see I've got my average rate of change is the change in my heart rate divided by the change in the time. And we don't have a function, so I can only represent that as the function value of my heart rate at 90 seconds minus my heart rate at 0 over that 90-second period of time. So this would be, in our heart rate would be in beats per second if we needed the units on that. In example 3, a hypercoaster is a special circuit roller coaster with a height measuring larger than 200 feet. And if we have a hypercoaster under design, we're going to put this function into our calculator here, 1.87 x to the third minus 20.64 x to the second plus 112.79 x plus 132.56. Okay, and we want to find the average speed of the hypercoaster from 2 seconds to 8 seconds. So the average rate of change, I don't really need to adjust the window. We can just come over here and let the calculator do it. So we want the function value at 8 minus the function value at 2 divided by 8 minus 2. So that looks like about 63.47. Whoop, sorry about that. Okay, so about 63.47, and our units are in feet per second. Feet per second. We don't have a third decimal here. What's the average speed of the hypercoaster from 4 seconds to 6 seconds? So just repeating that. I'm going to grab this expression and paste it and put from 6 seconds to 4 seconds, and do the same thing down here, 6 minus 4. And it looks like we got 48.51, dropping at 48.51 feet per second. So in explaining that, we could say the average rate of change on the time interval from 4 to 6 seconds is about 48.5 feet per second that the hypercoaster is dropping. Excuse me. On part C, estimate the instantaneous speed of the hypercoaster at exactly 5 seconds. So you can see what we're doing, the same as the Tower of Pisa. So stop the video and calculate that, and then come back to see if we have the same answers. So does your chart look like mine? And then part D, explain the meaning of the instantaneous speed in context of the question at 5 seconds. So the rate of change, I said the rate of change and the drop of the hypercoaster at time equals 5 seconds is about 46.647 feet per second. Okay, I live in Orlando, Florida, the city beautiful, and we have lots of traffic at the Orlando International Airport. So this example is talking about the traffic pattern of the cars that are leaving the departing flights lane at the airport. Whoop, I got sign inverse there. Don't want sign inverse, I want sine of x over 3. And we'll have to adjust the window so we can get a sketch of it. I believe they want us to sketch it. So that's under menu 4, 1. I set my settings from 0 to 30 minutes. And I've got the height at about 70. Whoop, whoop, don't want that. About 70 up to, I don't know, 110. And I added and subtracted 92 and 15. So we're going to use that in a minute. But they want us to find the velocity at 18 minutes. So we could do that over here on the calculator page. And since it's got a sine function, I'm going to put a decimal after the 18 so I get a decimal answer. It's one of the features of the Inspire you need to know about. So the vehicles at 18, I said velocity, I meant vehicles, at 18 minutes is going to be calculated by 92 minus 15 sine of 6. And my calculator tells me that's about 96 vehicles per minute are going through that departure lane. Right? So we could just round that, about 96 vehicles, cars and trucks, buses, vans, everything. Okay. I pre-drew my graph with 92 being on the y-axis for vehicles, and there's our 96 vehicles at 18 minutes. Vehicles is on the y-axis. This should be minutes down here on the x-axis. So forth. So part C, we want to know what the average rate of change of the vehicles at the departing flights would be over a 5-minute interval. And we can use the calculator for that as well. So the vehicles at 20 minutes minus the vehicles at 15 minutes divided by that 5-minute interval, 20 minus 15, is a negative number. So 3,99923. So we could say the average rate of change on that 5-minute interval between 15 and 20 minutes inclusive is decreasing. Since our average rate of change is negative, the traffic is decreasing at a rate of about 4 vehicles per minute. And then part D, again, we're getting our time interval to be closer and closer to the exact amount. Once again, turn off your video and make the calculations and then check back in. So did you get close to me or the same as mine? I've got the instantaneous rate of change, that's going to be down here. The instantaneous rate of change at 18 minutes is decreasing at a rate of about 4.801 vehicles per minute. And then our very last question, why can't the instantaneous rate of change of traffic in the departure lane with respect to time be calculated using the method we used in Part D? Well, because again, that's going to cause division by 0. That would not be a valid solution. Later in our course, we're going to figure out that 0 over 0 is called indeterminate form. And that's the end of our first lesson. Welcome to calculus. See you next time.